Hello everyone, welcome to the Workflows4s DevLog. Today we have two topics. The first, the primary one, is collecting workflow instances, and the second, connected one, is the refactoring around unifying workflow instances. And as usual, let's start with why. What problems are we trying to solve today? So the first one is interrupted executions. So if you want a more detailed explanation or written down, it's available on GitHub. But the bottom line here is that if the workflow was woken up, so if the wake up method on the workflow instance was called, this means the workflow started doing something. But then at any point in time, the JVM might die, the machine might die, and then how do you know that your workflow can run again? How do you know that it has to be triggered? Okay. So as you probably know, the Workflows4s does nothing or very little on its own. So the user is responsible for waking up instances to trigger them to do something. But to do that, they need some sort of information on when is the right moment to wake it up. And this is the primary reason. But there is also the second reason. As some of you may know, the Google Summer of Code is starting today, and one of the projects there is the web UI for Workflows4s. This means that hopefully we'll have a nice user-friendly interface that shows us the running instances. But to make the UI actually useful, we need a sort of a registry, a sort of a something that will allow us to list, query the instances, because how else would you know which workflows you would like to observe? And because of the modular nature of Workflows4s, this is not something built in. This is not something that you have to use. Instead, we'll see that this is something that you can opt in and leverage if you need it. Okay, so let's see how this was implemented. If we look at the WorkflowRegistry object, we'll see a very simple trait that for a given ID takes the execution, takes ID, execution status, and does some opaque operation. Very, very simple. Now, the execution status that it takes is one of the three cases: running, awaiting, finished. Running is whenever something starts running. Okay, so if the workflow is executing something, this will be registered as running status. Now, if it's awaiting something, being a signal or a timer, then this is awaiting status. And when it's finished, it means there's nothing more to run. And we could stop here, because that's the most important part of the change to discuss today. So how is it used? This is called from the workflow instance, where we see whenever we are waking up the process, assuming there is something to wake up, there's something to execute. Before executing the code provided by the user, we register the instance as running. And as soon as there is nothing more to execute, we say that the instance is no longer running. How do we know if it's finished or awaiting? If the whole wheel currently stayed within the active workflow is executed, this means there is nothing more to do. And otherwise, it means we are awaiting something. Cool. So the change itself is not very big. But you might have noticed that that's just an interface. So let's look what implementations of that interface we have. So the one thing is no operation registry. We have to specify it, but you might not want to use it. That's why we have it. Another thing is that another one is in-memory workflow registry. So in that case, it collects everything that is possible and exposes it directly. This is meant primarily for testing purposes. And there is a third one, which is Postgres workflow that is very specialized implementation that collects information only about running instances. So if you look at the implementation, it drops everything from the table that is not running. That's to keep the table small and possibly support infinite number of instances. Now, that's all. Those are all the implementations that we have. And you might think, okay, but isn't that a bit too little, too few? And the catch here is that this part of Workflows4s is meant to be implemented by the user. So in your system, you might want to collect various informations about your workflows, connect it with some other information, store it in whatever way you prefer. And I would also say that storing a single enum in the storage of your choosing is not a problem for anyone integrating Workflows4s, anyone using Workflows4s. So I assume that all of the users can write this, can implement this interface. And that's not a big burden. And the extensibility and flexibility of that approach is more valuable than any predetermined implementation that we might support, provide. So in Workflows4s, one of the core principles is that the user is in control. We don't want to build a framework. We don't want to build a tool. It's a library that you need to understand and integrate properly. Okay. So now with that being covered, maybe we can also say a sentence or two how it relates to the web UI. So in the web UI, we will need another interface that can query the processes. So most probably we'll expose it. So whenever you want to use the web UI, you will have to provide something like queryable workflow registry that will the interface will provide. But we'll see when it comes. Okay, and now we can go to the more boring part, but also the more substantial, which is the refactoring that was required for that registry to come. So it was a separate pull request. If you're interested in what has changed there, you can take a look. But the thing is, now that we did that, we wanted to introduce the agent. The agent has to be called from WorkflowInstance, but we have at least 4 different WorkflowInstance implementations. So how do we ensure that it is called from all of them in the right moment? And that's why it was introduced something called WorkflowInstance base. This is more or less a usual example of a template method pattern, if I remember the name correctly. So we expose some lower level methods that has to be implemented by the implementation, and we use them to implement higher level methods coming from WorkflowInstance. Yes, I have some refactoring to do. Abstract givens are deprecated. Anyway, so what lower level methods we have here? We have lock and update state. We take a function, it takes the current state of the workflow, and it produces an effect containing the log outcome. The log outcome is either a new event or no op. this means, and when this is executed, we provided the update function, and when the log is finished, it has to give us the answer, which is like the state was either updated, old state, new state, or not. And then a method to get the current workflow. This, as we'll see in seconds, could be implemented in terms of update state, because it's just a simpler equivalent without logging, or with immediately finished log. The problem is that we don't want to log the workflow in case we don't need it. For example, when we query the state, we just want to get the workflow. We don't want to log it. So other usages might be allowed at the same time. So maybe before going further, why do we need to log the state of the workflow? Why we don't allow two instances to concurrently modify the same workflow instance? So let's imagine a case where we do the normal processing and we do an interruption. And interruption, like we have two signals, one through the ordinary flow, the other through the interruption. Now, if both of them start executing, they might execute some side effectful operation, and then only one of them can be picked as the right one. Only one event can be persisted in that case, because otherwise, how do we know which path to go? So that's why we have a locking mechanism in place. That's why we ensure that only one instance can modify the workflow state. How it's used, we'll see in a second. So what else? What other lower level methods we have here? We have an knocker wrapper responsible for wake ups. We have a clock, and we have the registry. Now maybe a small digression. There is probably a follow-up refactoring coming, because this is not very extensible. For now, we hard code each and every dependency in this implementation, and this means it might get problematic to add more, especially from outside the Workflows4s code base. So in a perfect world, we would have some sort of hooks that you can plug into, rather than requiring all them to be known here. But it's not that easy, so it's okay. So how do we implement different methods of work? We have the query state. We just get the current state of the workflow. We get the current time, and we produce the state. We query the state for the state. This is for the user-defined state. Okay, how do we get the progress? In a very similar way. How do we deliver a signal? So we take the current time, we log the state, and process the signal. What it means? We pass it to the active workflow. We get the result. It's either some I/O to execute or nothing. If it's nothing, it means that the signal was unexpected. If it's I/O, we lift that I/O to the effect type of the instance, and that's it. Return the new event persist. How do we handle wake-ups? In a similar way. We lock the processing logic, and we do something after the event. So this is very similar to the signal. We say that we proceed, and we get some I/O. We might get some I/O to execute. Now is the important bit. Before the I/O gets executed, we mark the instance as running. We execute the I/O. We get the event, and that's it. Okay. Now, the next one are just, there's no next one, there are helper methods. So how do we get the current time? This is a small trick that hopefully is good enough to use. So we are using a clock, and to maximize flexibility of the library. We are using Java clock, not the cats effect clock, because eventually we want to have effect polymorphism. We want to have as little dependency on cats as possible. So we are using just the Java clock. Yet it's unsafe, and we want to have referential transparency, at least when the instance is using a referentially transparent effect type. So the proper way to do this would be to use a sync type class here that allows us to delay the execution of the clock instant. But we don't want to enforce such a strong constraint. There are many more data structures that can implement monad than that can implement sync. So we are using a relatively dirty trick here. So we are producing a unit and mapping it to get the instance. Assuming that unit is lazy, the mapping over it should also be lazy, and this should be referentially transparent. Cool. Here, this method we have seen called from both signal handling and wake up handling whenever a new, whenever the lock has finished. So we have the state update, and we see if the state was updated. One thing we do is we check for the wake up time. So if the new state has a different wake up time than the old one, we execute a knocker up. And another thing we do is we trigger another wake up. So this is something that might change in the future. I'm not yet certain about this piece of the design, but for now, the wake ups are chaining, in the sense that if you have 3 IO steps in sequence and you trigger wake up on the workflow instance, you will eventually execute all 3 of them. This might change when we, for example, do a retrace. We'll see, or from different reasons. But for now, that's the case. And that's it. So let's get back to our agenda. You have seen the instance base. So the workflow instance base was introduced to make sure, or rather make it easier to ensure a specific logic in the instance, to make sure that all the instances follow the same patterns. And for the same reason, we introduced a workflow runtime test. So a suite of tests that can be executed for any runtime. Those are then run for all in-memory sync, Postgres, Pekko. So for all those instances, we run the same tests just to make sure that they work as we expect. And you may wonder, why to do both? Why to unify on both the implementation level and test level? And the answer is because those are 2 separate things. One thing is that we decided to reuse the implementation. And the second thing is we want to assure that they all follow the same behavior. They all represent the same behavior. So at some point we might decide, okay, the decision about the common implementation was not correct, but we still want to make sure that it follows the same behavior. It represents the same behavior. So we can see it as double precaution. Okay. Now, something I forgot to put on the agenda, but what I wanted to show you is the Pekko workflow instance, because it was significantly refactored in scope of that work. If you look at the git diff, maybe we'll see it. No, this is not it. Give me a second. I have to go to the previous pull request. But all the implementation that is here on the left was much simpler. Why? Because most of the logic lived something called workflow behavior. So this was executed on the Pekko side. This is the logic executed on the Pekko side. Whenever you spawn a Pekko actor, this behavior is passed there, and Pekko will execute the logic here on its own thread pool with its own all peculiarities, let's see. And now the implementation has changed, and a lot of logic was moved to the workflow instance. So that logic will no longer execute on the actor thread, it will execute on the instance, on the caller thread, which is better, at least from some angle, because we want to have the Pekko integration as lightweight as possible. It's easier to reason about the code that we have on our side than the code that is run by Pekko. So that's why this had to be refactored significantly. And maybe one more thing I want to show you is another workflow instance implementation, which is DB workflow instance. And it uses, under the hood, this very complicated type. Okay, some of you may argue that it's not that complicated, but for me, it's more complicated than it should be. But there is a relatively good reason to do it. So what is our effect type here? It's a classly, so a function from lift.io connection IO to connection IO of t, right? We could write it as lift.io connection IO to IO. Why do we use it? That's because we have to provide a lift.io implementation to the workflow instance base. We need ability to leave an arbitrary IO into connection IO, or at least into the effect type. And the easy win here would be to just make it an IO. Don't operate on connection IO. Say, okay, this is database-based workflow instance. It does operate on connection IO, but we transact it internally, and you just see the IO. And that might be fine. But I decided that's cutting corners. Because what if someone tries to run this logic from the instance transactionally within some other code with some other code of theirs? So that's why we really try to operate on connection IO here. But this is tricky because we need the lift IO, and to create a lift IO, you have to create something called cuts effect dispatcher. So basically a thread pool that will allow you to run this IO within the connection IO. And there are different ways to provide. So now let's maybe look at how this instance is used. So when you create a database runtime, we hide this complexity for you because most users don't want this transactionality. This is implementation detail, they probably don't want it. So what happens here is that we just give you the workflow instance of IO. And what happens next is that we take our workflow instance and we map it. So we have a functor k parameter, like functor k like structure, like this could be derived, but we just take a workflow instance for effect type f workflow and map it through a polymorphic function from f to g. And that's how we create workflow instance of g. And what we pass here as a function is that given our classly, we fill that classly with we create the lift IO, so a new dispatcher. We fill that classly with that lift IO, and we also transact the whole thing. So for now, this is the baseline implementation, but it's a bit problematic because this will create a dispatcher on every call, and this might be slow. But adhering to the philosophy of make it work, make it right, make it fast, for now, this is good enough. The alternative is to create a lift IO once when creating the whole runtime, which is fine. The problem is that this makes it harder to create the runtime, because when we do it, we would have we would create not a database runtime, but we would have to create a resource of database runtime, putting a little bit of complexity on the user side. So it will probably happen, but for now, we wait for someone to complain about this. This implementation is equally correct, although slower and more resource intensive. So let's see if anyone uses it, if anyone complains, and then we can fix it. And that's pretty much it. I think this was a rather long episode this time, but we covered quite a lot of ground. So to sum up everything, now we will have a new interface that allows to receive a call whenever workflow changes its state. So user can register that information in some way. And we saw how the workflow instance was refactored to reuse the same template method, to reuse the same logic across all the instances. Thanks a lot, and see you again.